So I present you with our code with a ginormous caveat in front of it. Do you know that word, ginormous? It's an expression that's a combination of enormous and gigantic. So my ginormous caveat is that I have learned R only within the last year. I am not good at it. And quite frankly, I don't like it. I don't. I've learned a whole bunch of different stats packages, and this one is always frustrating to me. So that is to say, if you look at this and you're like, why'd she do it that way? I know a better way to do it. Please tell me. You're probably right. One of the frustrating things about R is that you can do the same thing 18 different ways, and each is package specific. My frustration with respect to these sorts of models is that I'm very much used to having like one function that does all the things that I want. And that just doesn't happen in terms of longitudinal analysis or multi-level analysis in R. So I'm using a couple different functions within the NLME package as well as the LME4 package to be able to do these models. And I'll try to describe why that is as we go through it. So if you want to run the code with me, what you would need to change is inside the code, this part right here, I have defined an object that holds the path on my local directory to where things are. You would need to change that path to where you have downloaded this folder to, and then you can set your working directory to that place instead. But the original data are in there, and the rest of this, once you change that path, should run without a hitch if you want to run it along with me. So for ease of transparency, I am importing data from Excel. The story behind these data is that they're fake, but they're based on real data. So this is from chapter 7 of my book, continuing in chapter 9 for tomorrow. These are 200 fictitious adolescent girls measured approximately annually from ages 12 to 18. The outcome that we're predicting is risky behavior, which is a sum score because latent variables would be too difficult to do in one book. I wanted to get there, but I ran out of room. Basically, all the things that you don't want your teenage daughter doing. Smoking, drinking, shoplifting, et cetera, et cetera. Like we lump that into problematic, risky behavior as an outcome. And we would expect that that would increase over time as children get more daring and more autonomy. So that's what we're predicting. There's a time-varying predictor of monitoring that we will look at tomorrow, and there's a time-invariant predictor collected at the age 12 occasion about the mother's attitudes about smoking and drinking, where higher scores mean they have more conservative attitudes. And these data are based on real data for a study that was conducted at Penn State. And so this is, I simulated it so that people could have it for the book, but it is based on sort of a true story. And these are the packages in R that I used to do all of it, which are the top of the R syntax file loads and installs all of those packages if you don't have it already. Because I wanted to show the convergence between the MLM approach to doing this and the SEM approach, I'm using maximum likelihood rather than residual maximum likelihood. That's the only reason, because otherwise the numbers wouldn't match. Okay, let's see here, 4 o'clock. Hanging in there. Any questions on the story or otherwise before we look at it in more detail? Okay. So the first thing that I had to do is reshape the data. The way that the data were initially stored is in wide format, where it's one row per person, and it's separate columns for all of the variables across time. So I found a command within base R. I don't do the tidyverse, by the way. I prefer the messy verse. I try to stick with base R as much as possible. So some of this could be done differently using that code, but I like this one because it's a little bit more transparent. So I am reshaping the data from wide to long in this set of commands, where ID variable is person ID that tells it how the data are organized. So that will be the common linkage across rows from the same person. These are the column numbers that correspond to the exact age at which the child was measured. So it's approximately every year, but not exactly. These are the columns that correspond to risky behavior, and these ones are for monitoring. And so when all is said and done, I have 3 new columns in long data. One is called age, one is called risky, which is our outcome, and monitoring is another variable that we'll play with tomorrow. Occasion is my measure of which time is which, and these are the sequential indicators for that. And then I sort, and then I have to make some new variables in order to do the analysis. So I made a variable that is rounded age, which is occasion plus 11, so that I can get the means at each occasion out of a estimated model. I have time, which I am centering as age minus 18. So rather than having time 0 be at the beginning, I've chosen to have it at the end. The reason for that is because I expected that in this sort of context, it might be more informative to predict individual differences in their eventual risky behavior, because the 12-year-olds don't have that much variance. So there's a lot more variability in the data at age 18, so that's where I stuck my intercept. Attitudes is a mean across items measured on a Likert scale, and the mean was near 4, so that's what I picked, attitudes. And the way that I tend to name my predictors is that I stick the centering constant at the end. That way I don't have to remember what it was. So this process then gives me a new data set called example 1 in long format, so it will have 7 rows per child. Okay. So first step is just data description. I want to know what my fixed and random effects are trying to model. And so this model is estimated not for comparison purposes, but just for descriptive purposes. So I am using rounded age in this model. I am ignoring all of the unbalance in exactly when they were measured, just so that I can get a sense of what the trajectory looks like. So the model for the means, this should have a little hat over it. It doesn't register correctly on here. I have a fixed intercept, and then each of these things are dummy codes. So I'm treating age as a categorical factor variable. I am also going to estimate all possible variances and covariances across time, just so I can get a sense of what those look like as well. So this model does not have any random effects in it. This is the option 2 for how to model person dependency. Just do it as a multivariate, let all the variances and covariances be what they want. So this is for descriptive purposes. The only function that I could find that would let me do this is the GLS function that is within the NLME package. So I'm saving my results from this function with a model called SAT-UN, which to me means saturated means unstructured variance. I'm using maximum likelihood, as I said. And then here is the model statement. So this is just the fixed effects portion of the model. I'm keeping my general intercept, and then I'm treating rounded age as a factor variable. So the intercept is going to refer to age 12. And then these 2 lines, those give me heterogeneous variances as a function of age. That's the weights thing right here. And the correlation gives me all possible correlations between occasions separately. So those of you who've seen SEM before, who are my SEM folks? A few people? You know what this model is. This is your H1 model. That's what this is. All means estimated separately, all variances estimated, and all covariances estimated. So I could use the -2 log likelihood for this as a baseline for checking fit if I wanted to stick with rounded age, but in the models that follow, I'm going to use exact age instead. One problem with GLS is that it does not use the correct denominator degrees of freedom for these models. It uses residual instead of anything else. And so I have the note here, show results with incorrect denominator degrees of freedom. So this print thing, by the way, I have these throughout my code because in order to output the results to a text file and include the notes that I had included, rather than have them as comments, I do them as prints. Okay, I know that was a lot in a little bit of time, but are there questions about the code here so far? No? All right, here's what we get. So we have our fit statistics, AIC and BIC in smaller is better form, and this is our log likelihood in bigger is better form. These numbers don't mean anything in absolute value. They only have meaning in relative value as far as other models, so we don't need to worry about those too much. This right here is the lower interior off diagonal of the correlation matrix across time. So what I wanted to point out in looking at this is just stare at these numbers here, just eyeball these. Does it look like these correlations are the same across time or not the same? I'm just asking for an opinion. So you can't be wrong.
I mean, it's not the exact values, and it seems to increase with time. I would say not the same.
Yeah, I would vote for not the same. It looks like occasions that are the closest together are the strongest, although there's a little bit of weirdness, you know, in some of these. But then the further apart you go, the lower they are to some extent. So not the same is what I would vote for. What kind of not the same is what we have to figure out. So these differences in correlation across time, this indicates that something beyond a random intercept is going to be needed. Because a random intercept would say they're all the same. If the only way that people differed from each other is in means, these should all be the same, or close to it. Then it gives you this weirdness, which are the standard deviations for each occasion relative to one of them as an anchor point. That's very unhelpful, so I figured out a way to get something that's more useful in just a little bit. Here are my fixed effects. And this is out here is me trying to help. R did not label these for you. This is, as my students would say, Proc Lisa. But if R told you exactly what everything meant, then I wouldn't have a job. So we have the fixed intercept, and given that the rounded age variable first occasion is the reference, this is the risky behavior at age 12 specifically. And these are the differences relative to age 12 and risky behavior. So it looks like it is increasing over time, as one might expect. It also gives you the square root of the risky behavior variance at age 12. That would then be used to reconstruct what the actual variances are if you wanted to do the math. Instead, I asked it to show me the matrix in its correct form. So I used a function called getVarCov to create what is the marginal variance covariance matrix across time. So in this matrix, on the diagonal is the variance in risky behavior at each age. Do these look the same or not the same? Yeah, so the variances, they look reasonably similar to a point, but then they really increase towards the end. So variances that change in one direction like that, that's a dead giveaway that random slopes are part of the story. And since I simulated the data, I can verify that that is indeed the case. Simulated data behave very nicely. And the covariances are hard to interpret because the variances change, but you can tell that they're also not constant, in part because the variances are not constant. So point being, this is the answer key. This is what the random effects and residuals are going to be trying to recreate more parsimoniously than letting everything be estimated separately. Here are the correlations. So this is the full correlation matrix that it gives you just the interior part of earlier. So somewhat redundant, but helpful to see sometimes. Then I asked for the actual predicted means given by the model, put back together again from the fixed effects, and here they are. It would not let me use Satterthwaite denominator degrees of freedom to do the pairwise comparisons, but it did end up giving me an F-test of all the differences in the means across time with the correct denominator degrees of freedom. So this p-value matches what it should be across other programs. So here are the means that are implied by the fixed effects. So this is what the fixed effects of my growth model are going to be trying to recreate. And here's the pictures that I made with that. So mean risky behavior on the y-axis here. This to me looks sort of quadratic-y, but in a different pattern. It looks like it is increasing over time and more so at the later occasions. Here's the total variance in behavior across time, also increasing over time. So the fixed effects are in charge of recreating this pattern on the left. The random effects are in charge of recreating this pattern on the right. That's what they're for. So this type of descriptive process I would always go through as sort of a step one, because it can guide you as to which family of models is going to be most useful. All right, questions with me? So now we're going to go take everything out of the model and start building it layer by layer, starting with empty means. So here's my model. Risky behavior is a function of an individual intercept that is defined at level 2 as a fixed effect and as a random effect. And the font in this case makes the gammas look more like V's than Y's, but it's the same letter. So in the models that follow, I'm going to stick with a level 1 matrix for the residuals that has constant variance on the diagonal and zeros on the off diagonal. And that means that I can switch to Elmer, which is a function inside the LME4 package instead. It does not have the capacity to do any other kind of R matrix. All it lets you do is have residuals that have constant variance with no covariance. So Elmer is really designed more for cluster data than longitudinal data. The reason that I'm using it is because it does use the correct Satterthwaite degrees of freedom in computing the significance test for the fixed effects, whereas the GLS and LME packages are sort of hit or miss with that. So I'm switching the way that we're estimating it, which means the code looks a little bit different. Instead of having model, I think it was in GLS, where we go here? Yeah, it's model equals as the argument to the function. Here it's formula equals, but the rest of it is the same. So I'm saying that risky behavior is the outcome predicted by a fixed intercept plus inside the parentheses, the column of ones. Can you guess what that is? If this one is the fixed intercept, what do you think that one is? The random one, yeah. And what would happen if I tried to make it a 0? In theory, that should be possible if I wanted to take it out, but not in Elmer. It will yell at you and insist that you have it. So, 1 it is. So the output looks a little bit different. It gives you AIC, BIC, log likelihood, and then deviance, which is -2 log likelihood. So this is the value that you would use to do significance tests by comparing -2 log likelihood values. Then we get our variance components. So these are the parameters in the model for the variance. I have labeled these for you. So 10.8 is the amount of variability and risky behavior due to person mean differences. Some girls have more of it than others on average. 17 is the amount of variance that's due to level 1 with in-person fluctuation around those means, so time-specific variance. And I can use those two numbers to form an intra-class correlation. Here's the math. It's between over total, and there's a ICC function that I used here to make it do the math for me. Intra-class correlation is 0.39. All right. Tell me what that means, and I'll let us take another quick break. How's that for incentive? So interpret that number. Someone stick it in a sentence for me. 0.39 is?
There's 39%
Ding. Which means within is how much? The rest. Yeah, okay, yes. So 39% is between, and the rest of it is within. Very good. All right. How about we take like 5-10 minutes, stand up, wake back up again? Sound good? Okay, let's do that.